So today we shall start our discussion on fiber optic sensor. Last two classes we have discussed about laser-based sensors, which are basically some of the industrial applications I have discussed. Now, fiber optic sensors have also industrial and scientific and home applications as well. So there are types. There are various kind of fiber optic sensors are there. Some of the sensors are interferometric fiber optic sensors. So in which one arm of the optical fiber is perturbed and another arm acts as the reference arm. Then we have distributed fiber optic sensors. So because optical fiber itself is a sensor, and optical fiber being after coating, it can be quite flexible and can be laid down throughout a space along length of a bridge or around the rooms of various buildings. So it can monitor various parameters. One of the important parameter is temperature. Another important parameter could be stress or strain, which is distributed over length or space. So that has some advantage if we use fiber optic sensor instead of, say, other kind of sensors. There are other solutions like wireless distributed sensor can also be used for monitoring purpose, but truly distributed ones would be like fiber optic sensors because it is laid down in a continuous fashion. Then of course there are like laser-based sensor. Here is also intensity modulation-based sensors are also used. For example, microbend, because bending essentially introduces losses. So therefore, the change in intensity can be related to various physical parameters, stress, strain, or temperature. So that is the basic principle of intensity modulation based sensor. So we shall start our discussion with interferometric sensor. Fiber optic interferometric sensors are very sensitive, and many configurations are possible. Like Mach gender, Michelson, Sagnac, Pepri Parrot. So all these are basically various interferometric configurations. So all of these can be implemented using optical fibers. maybe we will take one or two example. So let us take one example of Mach gender for magnetic field sensor. So magnetic field sensor by Mach gender configuration. So the basic one configuration is like this. We have a laser diode here. So these are the 3 dB coupler. So we have a launching fiber at this place, which can be single mode fiber, and then we have a reference arm and a sensing arm. So here basically, yes.
Sir, 3 dB coupler means?
3 dB coupler means basically it will split the light in 50s to 50. That 50% power is essentially 3 dB point. So that way the popular name is 3 dB coupler. Basically it splits the light into equal to uh, these two arms. Okay, one is reference arm and another is the sensing arm. That splitting, the mechanism is very simple. If we this bending means there would be some modes of the optical fiber that will comes out. That becomes a not guided mode but a leaky mode. Now the concept is that if I have another waveguide which can support the same wavelength of the light uh, 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 as a waveguide, so that is also bend and come very close. This closeness is to be of the order of wavelength. So that means if I am here like 630 nanometer or zero point 0.6 micron, so it has to be 0.5 micron or 0.4 micron closer. So usually these two surfaces are polished and they put side by side through a gel. And depending on the length of this, actually the percentage of this, it goes up. There is some problem. Then similarly at the output we have that same coupler is acting as a mixer, where basically the two lights, one is having some phase. These two arms lengths are same, but if there is some perturbation here, there will be change in refractive index, so path length will change. And then this is mixed here at this coupler. So then there will be interference created and intensity modulation will be affected. And that intensity modulation will be detected by a photodetector. So the advantage is that as like optical interferometer, we can sense as low compared to the wavelength or a small percentage of the wavelength shift. So therefore, a very small magnetic field uh, will be sufficient to give a perturbation through this. Now, this sensing arm material is magnetostrictive, like nickel. For example, nickel. So therefore, it basically optical fiber when jacketed with magnetostrictive material is expanded mechanically in presence of magnetic field. That is the first effect. Then this expansion will create two effects. One is the change of length due to expansion, okay, or contraction, whatever is which way this jacketing is done. So mainly it will squeeze, so there will be expansion. So expansion will change of length will occur and also change in refractive index. So these two will give rise to the change in the path length in the sensing arm. Magnetostrictive material is expanded mechanically in presence of magnetic field. So this is, that is, it induces strain. And also refractive index of the sensing fiber changes due to induced strain and stress. Induced stress and strain. So that creates a change in path length. thereby change in phase. So now this relation of the refractive index change and strain is can be given by a tensor. Which is known as the strain optic tensor. Strain optic tensor. Now the change is related in this fashion: delta 1 by n square ij equal to Rijk into Ek. E is the strain, Rijk is the tensor of rank 3. Again, as we have seen in the piezoelectric case, here also, generally this part is simplified by taking some symmetry, assuming some symmetry of the stress and strain. Taking strain in Ij commutative, that is the index is replaced, Ij is replaced by a single index. That is 1 is replaced by 1, 2 is replaced by 2, 3 is replaced by 3, 2 3 and 3 2 replaced by 4, 1 3 equal to 3 1 replaced by 5, 1 2 equal to 2 1 replaced by 6. So then we have delta 1 by n square I I equal to 1 to 6. Pij and Ej. So now Ej or epsilon j, whatever is the strain, vector in xyz direction in the fiber. Now here again we can assume some relation that assuming 2E1 plus E3 equal to 0. That is constant volume, where this one is longitudinal strain and this is transverse strain. Delta 1 by m square 1 becomes equal to delta 1 by m square 2 equal to P11 plus P12 into epsilon 1 plus P12 into epsilon 3 delta 1 by n square 3 2 P12 epsilon 1 plus P11 epsilon 3. Assuming there is no shear, assuming no shear strain. So delta 1 by n square 456 can be assumed 0 if there is no shear strain. Because we have assumed that magnetic field is aligned along that vertical direction, so there is no cross component as such. Delta n1 is equal to minus half n cube into P11 plus P12 epsilon 1 plus P12 epsilon 3. So delta phi, therefore, phase change delta phi equal to twice pi will be there, then n into L divided by lambda. So for lambda, it is twice pi. For L, capital L is the length. So this is length. So NL will introduce twice by NL by this one. And then apart from this refractive index induced phase difference, there will be simply expansion related phase difference, which is in the longitudinal, which is nothing but the longitudinal strain. Okay. So therefore this multiplied by epsilon 3 is the first component, and then we have minus n square by 2 into P11 plus P12 epsilon 1 plus P12 epsilon 3. So basically this part is change in length, and this part is change in refractive index. Now for glass, the change in refractive index, that is the strain optic coefficient P, that is quite small, because most of our optical fiber are made of glass. For glass, P11 would be approximately 0.12 and P12 approximately 0.27. So therefore, if we neglect even the second term, refractive index term is neglected, the phase difference error will be within 10%. Delta phi would be approximately equal to twice pi NL by lambda to 0.92 epsilon 3. So, however, there are some more complication is there in this. Usually, these magnetostrictive materials are nonlinear in nature, because if we want a good effect, we have to put high mu materials like nickel. If we do not want say too much non-linearity, we may avoid iron-based magnetostriction. In this case, in that case, that will be very sensitive, but non-linearity will be too high. So nickel is a moderate one, but still there it has non-linearity. But if we want to reduce it further, we may have to use some special diamagnetic material where the linearity is further enhanced. Strain produced by magnetic field is related by nonlinear relations. So therefore, generally, therefore a zone of operation is selected by biasing the AC magnetic field, AC or DC, whatever, by biasing with the constant magnetic field. Either by putting a permanent magnet, by placing a permanent magnet, which of course need to be replaced from time to time, or by battery operated electromagnet. Now, basic advantage of this scheme is that this part is completely optical. Okay, so I have a laser here. This laser and photodetector can be kept on one side quite far, and then this launching fiber can have some 10 meter, 30 meter, or whatever be the length required. And then there is this device which is usually packaged in a vibration-free platform and an enclosure, non-magnetic vibration-free enclosure, because what happens that optical fibers or any interferometer is sensitive to vibration that changes the path length. So therefore it has to be put on a box, and then we have an aperture through which this magnetic field is induced, I mean to the sensing arm, which is exposed on a place of that box, and the whole thing is quite far. So this from this photodetector itself. So that means the electrical part uh, and this source and detector and also other kind of signal conditioning also is required, like amplifier, etc. Those are kept quite far. So therefore, these can be put in an environment which is very hazardous otherwise, and where maybe electrical appliance cannot be put in a safely, maybe in a nuclear chamber, or it can be put uh, in a very high current environment. So or high magnetic field environment where a lot of electromagnetic interference is there, because our basic signal is basically optical, and then within a box we have a small aperture. This size would be hardly a centimeter or so, and there this magnetic field is exposed, which is the background magnetic field that is uh, getting measured. If we want to enhance that some directed magnetic field, so of course we can put a coil instead of a to direct a magnetic field, uh, which can be used for current measurement as well. So this biasing is usually done by a battery operated electromagnet. That is because of the reason that we have not put any electrical connection to the whole measurement place of the sensing box, external electrical connection. Now for nickel, at high magnetic field, strain epsilon 3 equal to K1 h to the power half. This is when h greater than 1.5 or state. And for low magnetic field, compared to this reference of 1.5 or state, the magnetic field is much lower than that. In that case, epsilon 3 equal to K2 h square. So this is a saturation type curve. So where basically when the magnetic field perturbation is of lower value, then the variation is more in square terms, and it is saturating when the magnetic field is high. So it has been saturation is approximated by a square root here. A better approximation could be say exponentials, but for ease of calibration, manufacturers often use such kind of method. So a biasing magnetic field can be used H0 epsilon 3 is equal to K1 to H0 plus H1 sine of omega t, assuming AC magnetic field whole to the power half. If H0, the biasing field, is much greater than H1, then we can neglect this one. Epsilon 3 AC would be equal to K1 divided by 2H0 to the power half into HAC, that is H1 sin omega t. K1 for nickel is equal to minus 10 to the power minus 5 approximately. So for on the other hand, if we want to measure a small DC magnetic field, so of course these are the general measurement technique, biasing measurement to select a operating zone. Not only for this can be used for any measurement purpose as such. Where there is a problem of nonlinearity, so and the measurement is for a small zone, so we can select the appropriate zone. Epsilon 3 is equal to K2 into H0 plus H1 sin omega t square. Here the biasing field would be AC. So AC biasing field H1, DC field H0. H1 much greater than H0. Then epsilon 3 AC is equal to 2 K2 HTC HAC sin omega t. So here there are two, AC biasing has two advantages. One advantage is that it is amplifying the sensitivity, because as you can see that this one is 2K2 HDC into HAC, where this is the measurand here. This is the DC field we want to measure. So that sensitivity has been enhanced. And also because it is now modulated at a particular frequency omega, so therefore we can appropriately filter it out. So this omega is the omega of that biasing field. Now Mach-Zehnder interferometer is simple to construct, and because of the closed loop configuration it is also to some extent robust, but as I said it is dependent on vibration and also on temperature. So therefore usually the temperature of that interferometer is monitored. Now if there is so much problem, then why fiber optic magnetic field sensors are used? Because this is very sensitive. It can sense as low as the Earth's magnetic field as well. Since we are referring the change in path length with respect to the optical path length, a fraction of micrometer. The other configuration is of course possible with Michelson. The Michelson interferometer has the advantage of open loop configuration. I mean, apparently open loop, though all interferometer needs closed loop configuration. This is the jet diode. The launching fiber. Then we have that same coupler. Then on these are the mirrors. Difference arm, and here this is the sensing arm. Now this is a photo detector. Now this act as a coupler and mixer, that is splitter and mixer as well. So this length is made such a way that this gives a sense of direction. So usually these are known as directional splitter and mixer. So that means when light goes here, it will follow these two paths, but this path will be chosen when light is coming back. And then we have a photo detector. Lock-in amplifier to pick that modulated frequency at omega. And then we have output. So this are the advantage is that these mirrors are, though I have drawn like this, and they are simply metal deposition of the fiber which is cut, the glass is cut, and then you have make a metal deposition like nickel or silver at the surface of the fiber, so it itself acts as a mirror. So therefore it can be very compact. These two can be within a cable, and there would be an aperture here where this sensing field is exposed. So therefore this can be put in driven from one end inside into certain measurement place where the other side is not accessible. So that means these fibers, the out end of this fiber is not accessible. This is a rigid cable sort of thing which are driven through the measurement site. Okay. So then accordingly at various places while it is driven, the magnetic field will be calibrated or measured. So while it is entered from one end to the other end, so this magnetic field will be measured in terms of space. So many strategic application is there for such kind of measurement. So this is of course Michelson interferometer. So there are one I shall discuss about fiber optic gyro, that is Sagnac interferometric principle, which is also quite popular, and many inertial applications where we require rotation sensing of very small amount of rotation sensing. So their fiber optic gyros are nowadays used and slowly getting replacing the 6-axis gimbal based gyros. I think that we shall discuss tomorrow.